In the last chapter, we learned that we get a lot of information about the shape and the spread of the data, and that allows us to make general statements about the group that the data points are coming from. But now in this section, we want to ask the question instead, how do we make statements about individual data points within the group? So for that, we need a basis for comparison. We're going to use the standard deviation as a tool to construct a new measure called the z-score. The z-score is a score that goes along with each point of the data, where I take a data point minus the mean and then divide that result by the standard deviation. And what that does is it turns all of my data points into these standardized values, or z-scores. So written out, the way we calculate a z-score is we do whatever our data point is, subtract the mean, and then divide that result by the standard deviation. Standardized values have no units, but those z-scores are measuring the distance of that data point from the mean in terms of standard deviations. So a negative z-score would tell us that we lie below the mean, and a positive z-score tells us we lie above the mean. So the standardized values have been converted from their original units to the standard statistical unit of standard deviations from the mean. So z-scores don't have any units. That allows us to make comparisons between different populations or items measured on different scales or with different units. The z-score can give us an indication of how unusual a value is because it tells us how far it is from the mean. Negative is a distance below the mean, positive above, and the larger that the absolute value of it is, the more so it is in that direction. Now we're going to define exactly what we're going to classify as an unusual score coming up, but it allows us to know in general, is this in keeping with the bulk of the data or is it far away from the data? So there's no universal standard for z-scores, but there's a model that shows up over and over in statistics called the normal model, or a bell-shaped curve. The normal models are appropriate for distributions whose shapes are unimodal and roughly symmetric. These distributions provide a measure of how extreme a z-score is. Here's an example of that bell-shaped curve. Every distribution that is unimodal and symmetric will have a different bell-shaped curve that can be drawn to it, but they're all different normal models. They're defined by a mathematical equation that determines that normal model based on the individual mean and standard deviation of the data set that we're dealing with. So the way that we write this is function notation. If you remember your algebra, the n is the name of our normal model, so capital N is our function name. And then the parentheses, inside the parentheses are a function. This is a function of two variables, the population mean and the population standard deviation. So the sample mean and standard deviation are written with Latin letters. Our population mean and population standard deviation are written with the Greek letters. So here's our z-score written out with the Greek formula. The one we did before was with the Latin formula. Once we've standardized, we only need the model that has a mean at 0 and a standard deviation of 1. That's what the standardizing does. It shifts the mean of our distribution to 0 and shifts the standard deviation to 1. Be careful, don't use a normal model for any data set. It needs to be roughly unimodal and symmetric. So how do we know if it is? Well, we've got the nearly normal condition that we require before we can convert to z-scores. This means we're looking to see if the shape of our data is unimodal and symmetric. We can check that with a histogram. When we are dealing with a distribution that is roughly unimodal and symmetric, it will follow the empirical rule, otherwise known as the 68, 95, 99.7 rule. That tells me that roughly 68% of the data lies within one standard deviation up or down from the mean, about 95% within two standard deviations, and about 99.7%, almost all values, will fall within 3 standard deviations of the mean. Here's that empirical rule written out. 68 within 1 standard deviation, 95 in 2, and 99.7 in 3. Now, remember, this is a symmetric curve. It's symmetric about the mean, about the center point right here. So that means I can divide each of these values in half, and half will lie on each side. So that means that 34% of our data should lie within 1 standard deviation below the mean, and 34% lies in 1 standard deviation above the mean, for a total of 68% between the two. Now remember, this is 95%, and if 68 of that 95% is here, that means 27% is left to be broken up over here and here. Well, half of 27% is 13.5%. So that's what goes in here and in here. And then, of course, doing the same thing, 95% of my data is here, but 99.7 is here. So that means 4.7% is on the outside. So half of 4.7% is 2.35%, and that's what goes here and here. So notice there is very little data in this area and this area. The large bulk of our data is in here. Okay, let's use this with an example. Suppose the heights of men have a bell-shaped distribution with a mean of 69 inches and a standard deviation of 2.8 inches. We want to know about what percentage of men would have heights between 60.6 inches and 77.4 inches. Well, now, if we look at our distribution that models this, we've got a bell-shaped distribution, a mean at 69. We're going to go up 1 standard deviation and capture 68% of the data, 1 above and below. 2 standard deviations will be 95, and 3 standard deviations will be 99.7. So to get to my first standard deviation here, I do 69 plus that standard deviation. And so that's going to give me 71.8. So 71.8 belongs here. So now if I add 71.8 plus that standard deviation again, I'm going to get to 74.6. That's my next value here. Now, adding 2.8 one more time will take me to 77.4, value that I'm looking for right here. Now, to get my values over here, I'm going to take and subtract that standard deviation. So I'm doing 69 minus 2.8. That's 66.2. And then the 66.2 minus 2.8. That's 63.4. And then if I subtract 2.8 one more time, I get to 60.6. So this question is really asking me about how much of the data should I expect within 3 standard deviations of the mean. And my answer there is 99.7%. So I would expect about 99.7% of men to have heights between 60.6 inches and 77.4 inches.